You know all those AI models we use every single day, from ChatGPT to Claude? They're all built on one core piece of technology. But what if that technology has a hidden, fundamental flaw? Well, a brand new paper is proposing a radical new design that just might change everything.
Right. So pretty much every AI you interact with is built on an architecture called the transformer. And this paper starts with a really provocative question. What if the most important part of the transformer, its attention mechanism, has been flawed from the very beginning, holding back AI this entire time?
Okay, so to really get why this new idea is such a big deal, we have to go back to the beginning and understand the problem they're trying to solve. Let's dig into this hidden flaw at the very heart of the attention mechanism.
At the core of every single large language model is something called softmax attention. You can think of it as the system that lets the model figure out which words in a sentence are important. It decides what to focus on when it's coming up with a response. It's basically the engine that drives all of modern AI.
But here is the catch. Here's that hidden flaw. It's called the softmax constraint. And what it means is that the math forces all the attention scores for all the words in a sentence to add up to exactly 1. It's kind of like a pie chart. The model only has a fixed amount of attention to give out, and it has to give a little slice to every single word, even if some of them are totally useless. And this creates a really weird limitation. The best analogy is a volume knob. You can turn it up, you can turn it down, but you can never turn it all the way to 0. The model is always forced to listen to something, even when all the information it's getting is complete noise. It just doesn't have an off switch.
So, naturally, the researchers tried to fix this. Their first attempt was a model called Differential Transformer V1. And it was a really clever idea, but it came with a pretty dangerous side effect. The model became incredibly unstable and just a nightmare to train.
And here's why it was so unstable. There was a component inside V1 that could, at times, amplify the output by nearly 100 times. This created something called massive gradients, which is basically the model's learning process just going completely haywire. This kind of numerical chaos makes training these things at a huge scale practically impossible.
And this is where Differential Transformer V2 comes into the picture. It's a super elegant and powerful breakthrough that manages to fix the problem without all that crazy instability. The core idea behind V2 is, well, it's surprisingly simple. Instead of doing one attention calculation, it does 2. Then it learns a special value, they call it lambda, that basically acts like a tiny dial to control how much of that second attention result gets subtracted from the first one. And that simple act of subtraction, that's the key to this whole thing.
So look, if the first version, Diff V1, was like a powerful but unstable engine that just kept spinning out of control, then V2, well, V2 is a finely tuned F1 car. It gets rid of that unstable component completely and gives each and every token its own precise control over the subtraction. What you get is a system that's both incredibly powerful and perfectly stable.
And here is the real magic. This subtraction allows the model to finally do what it could never do before. Turn that volume knob all the way down to 0. This completely gets rid of a problem called attention sinks, which is where the model just gets stuck focusing on useless junk. It's like finally being able to tune out that one really loud, distracting voice in a crowded room so you can hear what matters.
So, okay, we have a more elegant architecture. That's cool. But what does that actually mean in practice? Well, the benefits are pretty clear. It's smarter, faster, and way more stable.
The list of advantages is really compelling. First off, it's just as fast as a standard transformer when it's generating text. No slowdown. Second, the training process is so much more stable, which, let me tell you, is a huge deal for researchers. It's also simpler to build, and as a little bonus, it works with existing optimization tools like flash attention right out of the box. Now you might be asking, how can it do more work without being slower? Well, the trick is really clever. It adds more processing power to the part that understands the input, but not to the part that creates the memory bottleneck during generation. This means it gets to be more expressive without sacrificing any speed. It's the best of both worlds.
Of course, this all sounds great in theory, but how does it actually perform? Well, the early results are looking very promising.
After being trained on a massive 1 trillion tokens of data, Diff-V2 showed a really significant improvement in what's called language modeling loss. Now, this is just a fancy way of measuring how good the model is at predicting the next word. A lower score is better, and in the world of LLMs, a drop of 0.03 points is a really big deal.
At the end of the day, a lower loss just means a smarter model.
And as you can see from this chart, Diff-V2 consistently outperforms the standard transformer. It's proof that it's fundamentally better at understanding and generating language.
And it's not just about the final score. The entire process of training the model was just smoother. The researchers saw way fewer of those chaotic data spikes, even when they were pushing the model really hard. It's simply a healthier, more robust architecture from the ground up.
So, a small architectural change, a better training score. Why does any of this matter for the future of AI? Well, the bigger picture is actually where it gets really exciting.
For starters, it's just more efficient. V2 saves about 25% of the parameters. You can think of those as the model's building blocks in the attention part of the model. That is a huge saving that can then be reinvested to make other parts of the model more powerful, all without making the whole thing bigger.
There's a fantastic quote in the paper where the researchers basically say that even if the model performed exactly the same as the standard one, it would still be worth it just because the training is so much more stable. And that really highlights a key part of modern AI research. Reliability is just as important as raw power.
And that's really the bottom line. Foundational improvements like Differential Transformer V2 are what paved the way for the next generation of AI. By making training more stable and more efficient, they allow us to build models that are not just bigger, but also smarter and more reliable, and to do it faster. So it leaves us with this fascinating thought. We always imagine that breakthroughs in AI have to be these incredibly complex, mind-bending new ideas. But what if the next great leap forward is unlocked by something as simple and as elegant as a single subtraction?